Assignment 11, question 1. First, let me say, make sure you've watched both the video on torque and rotational inertia at least once. And over the course of the assignment, I think most of you would benefit from watching at least twice. Those two videos together are less than the time of a single lecture. So the first question is distinguishing between these two equations. And it's pretty easy, multiple choice questions, you can do it. But supposing on the final exam I ask you to write an essay or a paragraph about each equation, what are you going to say? So this is what you should say. The first equation is the definition of torque. And it's also the way of calculating torque. Torque depends on three things. It depends on the applied force. It depends on the distance. Don't call it a radius. This is a distance vector. The distance between the axis and the point of application of the force. And it depends on the angle between these two vectors. This notation R cross F is a Calc 3 vector product designation. And you might as well get used to it. What the cross product means is you multiply two vectors by each other. Means that you multiply the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them. And what that means is that the biggest number you can get is when the sine is 90 degrees and the sine is equal to 1 at 90 degrees or pi over 2 radians. So torque, this is the definition. These are the three factors that affect the magnitude of the torque. Equation 2 is the relationship between the sum of all torques acting on an object and its angular acceleration. So if the sum, so this is a relationship. It's not a definition of torque. It's not a definition of angular velocity. It could be taken as the definition of rotational inertia, which is the resistance an object has to angular acceleration. So the sum of the torques will equal the rotational inertia times its angular acceleration. This is parallel to the sum of the forces equals the mass times the acceleration. And of course, to fully understand this, you have to understand what I is, but that will come later. Okay. So question 2 is a way of understanding the torque equation, and the three things are the R, the F, and the angle. So two equal forces acting at the same distance, right? The distance from the axis to where the forces have equal magnitude forces, equal distance from the axis, but this one's at a smaller angle, right? The angle, this one's at a sharper angle closer to 90 degrees, but not 90 degrees. So this is a bigger torque compared to that one. Of course, these are 90 degrees and they're further away, so there's the R vector. These are the F vectors. The angle's 90 degrees. And so these torques are both equal, same R, same F, same angle. But if these two forces are equal, this is going to be a bigger torque because the R vector is bigger. And this has the biggest R vector, and the force, same magnitude of force, but the angle is 0 degrees. So the R vector is this way, the force is that way, the sine of 0 is 0. Obviously, this force does no twisting of the wrench. Question 3 gives us another way of thinking about torque. So in this problem, we have the axis, we have the R vector, and we have the F vector. So ignore these two other blue vectors. This is R, and the force is this way. So if we take R times F times the sine of the angle between the R and the F, or this angle, we'll get the torque. But another way of thinking of it is if we take R and multiply it by the sine of the angle, in this case it's not theta, it's phi, we get this. And this, if you take the line of action of the force and you take this L, which is r sine theta, that's perpendicular to the force. And so that gives us the torque. So this is just another way of thinking about r f sine theta. Could be the perpendicular component of r to f, or in the next case, the perpendicular component of the force to the r. So here's the r. This is a little bit easier to think about. This force has a perpendicular component and a parallel component. And as we saw before, the parallel component does not contribute to the torque. That would be f cosine of phi. But the f sine of phi gives us this perpendicular component. And so this is how much of the f. This part of the f is what's doing a torque at 90 degrees. So notice you have three separate ways of thinking about torque. And that's what this question is all about. Question 4 shows you 4 equations, all starting with I. I is the symbol for rotational inertia or moment of inertia. Moment of inertia is a more common term. Rotational inertia is more descriptive. Inertia, remember, what is inertia? I hope you remember. Inertia is the resistance to change in velocity or acceleration, inertia. But rotational inertia then is resistance to change in angular velocity or resistance to angular acceleration. In other words, how hard is it to get an object to spin faster and faster, or to get an object to slow down or speed up its rate of rotation? And like forces, right, a rotating object will continue to rotate, but if you want to slow it down or speed it up, you want to change omega, its angular speed, or give it an acceleration, you need a torque, and this is how much it will resist. So what are these? This is the equation for a point mass. That's the mass of the mass, and that's what? The radius? No, don't say radius. It's the distance from the mass to the axis. And what's this? Well, if you have more than one point mass, then you add up the inertia of each point mass. Just like if you want to know the total inertia of a series of masses, you would add up all the masses. But in this case, we have to add up all the inertias from 1 to however many they are, and we simply add them. And if we want to do the problem, as you'll see, if the problem is not point masses, we can artificially make it into point masses by cutting it up into pieces and doing a summation. Or, if we want to use calculus, we can cut the object into an infinite number of infinitesimal pieces, do this product of m times r squared, and add those infinite number of infinitesimal pieces. That's what the integral is. It's an infinite summation. And finally, for special situations where the axis is not at the center of the object, like in the case of the rod, and we want to know how does the inertia change if we move the axis away from the center of mass, then how far we move it will increase the inertia. So let me give you a few examples of all this. By the way, that last equation is called the parallel axis theorem, as you'll see when I demonstrate. So here's a thin rod, thin because just it doesn't have, it's strong but thin, so it doesn't have much mass. Here's an axis, so if we want to spin the rod, it'll spin quite easily. There'll be a little bit of inertia, but not much. But what happens if I put a mass on there? And just to keep it balanced, I'll put, so you don't think about it being lopsided, I'll put two masses on there. And so that adds some inertia. This will add more inertia, makes it a little bit harder to twist. And since these are relatively small, they're not exactly points, but they're relatively small, we can simply use equation 2. We can go m r squared for that one and m r squared for that one and add them together, and that'll give us the inertia. And yet if we keep the same two masses but slide them further out on the rod, assume they are the same two masses, they look a little different. Now we have more inertia, right? This is going to be harder to twist. The mass is the same, the total mass is the same, but it's going to be harder to twist. The inertia is the same, but the rotational inertia is different because that depends on the position. And so now we would do m times that r squared and m times this r squared. And since this is twice as far away, this is actually going to have 4 times more inertia. And if we put a bunch more masses on there, we can do mr squared for each one and add all 7 of those masses together, and we're fine. We got the total inertia. Okay, I went well beyond the scope of question 4, but all that information about inertia will be relevant to some of the later problems. So 5 is a simple torque problem. I don't think you should have any trouble with that one. And 6 is another wrench torque problem. So you should be fine with those two. And question 7 is a disc with 3 forces acting on it, so that's 3 torques. And so to get the net torque, we want to sum up all the torques. So we could write it this way: sum of the torques equals torque 1 plus torque 2 plus torque 3. That's what we want to do. And so torque 1 in this case is F1 times R1. Torque 2 would be F2 times R2, and so on. So let's look at that. Notice the angle between F1 and F2 is actually, it's 150 degrees, because if I take this vector R and slide it so it's tail to tail, that's the angle. But the sine of 30 and the sine of 150 are going to be the same thing. And so it's going to be R times F times the sine of 30 or the sine of 150. In this case, in the case of 2, the R and the F are perpendicular to each other, so that's the sine of 90. And in this case, the R and the F are opposite, so that's an angle of 180 degrees, and the sine of 180 is 0. So this torque clearly gives you 0 torque, and so F3 will be 0, and you add up the other 2 torques. And remember, if we didn't say it already, counterclockwise is positive, and clockwise is negative for torques. It's true of anything, right? If we rotate if we go through an angle this way, we call that a negative angle. An angle this way would be a positive 45 degrees. This would be a negative 45 degrees. So you don't really have to memorize this. Just remember the direction we measure angles. Counterclockwise is positive and clockwise is negative. And so you add those up and you'll get the sum of the torques acting on this disk. Okay, another torque problem where we don't really have an object, but you can think of this as an object and 4 forces acting on it. give you 4 torques, so we'll approach it the same way, where you will add 4 torques. So the total torque, if we take torque 1, we have R times F times the sine of 90 degrees. It's not marked, so we'll take it, looks like 90. And that's a negative torque, right? It's clockwise. So that's negative torque here. Then we go to force 2, that's counterclockwise, so that's positive. And we have 2 times F2, but don't use the 30 degrees, right? Because it's this angle here that you want. And what's that angle? Well, if that's 30, that's got to be 60 degrees. So you want to use the sine of 60. If you use the sine of 30, you're going to be in trouble. Remember, that angle is always the angle between the R vector and the F vector, and this is positive. And then F3 makes an angle of 100. Well, actually, it doesn't make any angle. It acts at the center, so the R is 0, right? The distance from the center to where the force is applied is a distance of 0, so when R is 0, the torque is 0. So torque 3 is 0. And torque 4, once again, we don't want the 20 degrees. We want the angle between the R and the F. So I'll let you figure that out. Haha. And F4, R4 times F4 times the sine of this angle. And it's a negative torque, right? It's tending to rotate the thing. It's going to rotate, that alone would rotate it clockwise. So this looks a little bit like what I talked about back in problem 4 on inertia. And so we have something that has 6 point masses and a rod, where the rod has some mass, so we have to consider it, and I'll talk about what we'll do with that. So there's actually 7 objects we have to add together, and so the inertia is going to be this summation. Well, actually, this is the summation of point masses plus a rod. So if I were to write this down, so torques are vectors. When we add them, we do have to pay attention to direction. And in our case, it's only 2 directions, either clockwise or counterclockwise. But when we add torques, torques are never, they're not vectors. I mean, inertia, when we add inertias, they're not. So this consists of 7 pieces. So we have I of each point mass, 6 of them, and we add those all together. Plus we have to add the rotation or inertia of the rod. So each mass, like M1 is just going to, I1 is just going to be M1 times R1 squared. So M1, these are all 200 grams, so 0.2 kilograms. And these intervals are all 10 centimeters, so we have 5, 10, 15, 25. So this is 0.2 kilograms times 0.25 meters all squared. That'll be the inertia of that one, and this is going to be 200 grams at 15 centimeters, and this is going to be 200 grams at 5 centimeters, or 0.05 meters, right? Make sure you do that right. And then add them all together. Well, you can just do these 3 and double it, because they have the same thing on this side. And how do we deal with the rod? Well, from calculus, which I'll show you later, we get that the rotational inertia of a rod is 1/12 ml squared, where m is the mass of the rod and L is the length of the rod. And since we're given that, we use this equation to calculate this part, and then we add all the 6 parts together, and that will give us our answer. So 10 and 11 are a series of 6 different ways of rotating, or 12 altogether, ways of rotating this shape, which is a T. 2 rods welded together, where one rod is, well, the end of one rod is welded to the middle of the other rod, and the thing is rigid. And we're going to put an axis, say, through the center of one of the rods on the base of the T, or we're going to run the axis along the rod itself at the top of the T, or we place an axis here and the whole T rotates around that axis that goes through the end of the rod, and so on. And so how do we do this? Well, the inertia is going to be the sum of the inertia of both rods. And we know what the inertia of a single rod with the axis through the center is. All right, so we have I rod equals 1/12 ml squared. I rod through the center of mass, or the center of the rod, is 1/12 ml squared. That's a result that we're given. And then if the rod isn't at the center, so if we have a rod and we put the axis through the center, we know how to calculate it. We just use that equation. But supposing I take the axis, keep it parallel, and I move it over here. So now the axis is through the end of the rod. This is gone. We moved it, kept it parallel. That's the parallel axis theorem. We kept it parallel, and we moved it a distance L/2. So for that, we use the parallel axis theorem. So the inertia of this rod is going to be the ICM, which is this, plus the MD squared, which is the mass of the rod, times the distance we moved it, the D, the distance we moved the axis, which is L/2 squared. So if we add this together, right, just for this rod, we get 1/12 ml squared. For the center of mass, we're using the parallel axis theorem, plus that other factor, MD squared. So M L squared over 2, so that's going to be L squared over 4. So we have 1/12 plus 1/4 in effect, or 4/12. It ends up being 1/3 ml squared. That's the inertia of a rod, a single rod, with its axis about the end of the rod. Right, I just used the parallel axis theorem. Okay, let me just run that by you. That got kind of messy. So what are we doing? We're finding the inertia of a rod when the axis is about the end of the rod. So here's a rod, the axis is at the end. In this picture, the rod would swing in a circle in and out of the screen, going around in a horizontal plane, given that this is facing up. Or we could put the axis coming out of the page, in which case the rod would swing in a circle this way or this way, whichever we rotated it, about this axis. Either one of those is the same thing, and you'll see this kind of axis in the second set of exercises. So we used the parallel axis theorem, where we moved an axis from the center a distance L/2, or in this case we moved the axis from the center here a distance of L/2. And so I of a rod with the axis at the end is going to be I through the center, 1/12 ml squared, plus the mass of the rod times the distance we move the axis, L/2 squared, or L squared over 4. Those two fractions add to 1/3, and that's the result. So we use the parallel axis theorem to find that, and we can use this result in any of the problems that we have. We don't have to do that calculation every single time. Okay, one more thing that you need to know before we start these 12 things. When the axis, generally the axis is perpendicular to the rod through the center. That's the simplest case. And that's the 1/12 ml squared, where it goes through the center of mass of the rod, and it's perpendicular to the rod. And if we put the axis at the end, either end, it doesn't matter, then the inertia becomes 1/3 ml squared. But what happens if we put the axis right along the rod itself? Well, since it's a thin rod, all that mass is so close to the axis that it offers negligible inertia. And the thinner the rod, the closer it is to being zero. So in the ideal limit, when we put an axis along the rod, the inertia of that situation is going to be considered to be zero because the rod is so thin, it's just very easy to spin it when the axis goes right through the center along the length of the thin rod. So these are the three equations we need. Plus, as you'll see, we still need the parallaxis theorem. Okay, I'm not going to work through all 12 examples, but let's do a few and then see how you can do. So let's do A. Here it is. The T section, there's the axis. So the total inertia of any of these is going to be the sum of the inertia of the vertical rod and the horizontal rod, and those will vary depending on where the axis is, right? The inertia of any object depends on where you put the axis. So in the case of the vertical rod, the axis does go through the center of mass, and so the inertia of that part of it is just 1/12 ml squared. And then we add to that the inertia of this rod, and you see the axis doesn't even go through it, but since this is all welded together, that is going to rotate around the axis as the shape rotates around the axis. So we need to use the parallaxis theorem for the horizontal rod. So let's move the axis so it goes through the center of mass. That would put it up here. So the parallaxis theorem for the horizontal rod says that the inertia through the center of mass here would be zero. And then we move the axis from the center down here. This is the real axis. So we moved it L/2. So that's this term. So that's plus m L/2 squared, or L squared over 4. So we actually have three terms. We have the term for the vertical rod, and we have the two terms of the parallel axis on the horizontal rod, and one of those terms is zero because the parallel axis through the center has an inertia of zero. So when you add the 1/4 and the 1/12, once again you get 1/3 like we saw before. Let me comment on the others, and I'll do one more. So B, you can see that the vertical rod is going to be zero because the horizontal rod is going to have an inertia of zero because it goes through the center, and the axis is about the end of the vertical rod, and so that's going to be 1/3. So it's going to be 1/3 plus 0. And this one has, for the horizontal rod, the axis is through the end, and so that's 1/3. And here the axis, it's like we did here, right? The axis, we used the parallaxis theorem to slide it over L/2 here. And so for the vertical rod, we're going to get the same thing again. We're going to get 1/3 because that's what we got in that problem. And you can probably see that these two are the same, just the axis is at the other end, and still the same distance from the vertical rod. And here you have one through the center of the horizontal rod and along the length of the vertical rod, so that's 0 plus 1/12. Let's do this one. Try and do this one and see if you can get it, and then check what I do. Do it first. Okay, so be methodical. It's easy to make mistakes. You got a lot of things to keep track of. So when you're doing this one, I did the vertical rod first. And for the vertical rod alone, the axis is through the end, so that's the 1/3. no reason to write the ml squared anymore because all we care about is the fraction. And then for this one, we need the parallel axis theorem. So if I slide the axis up here, when this axis is through the center of the horizontal rod, the ICM is 0. And then we move it, how far do we have to move it? Well, we move it a whole distance L. And so it's the mass times the length that we moved it, the distance we moved it squared. And so that's L squared. And this we said was 1/3 ml squared, so it's 1 plus 1/3 because this is 0. Okay, let's go to the other set. Okay, this is the other set. Let me reduce it in size a little bit. And which one do you want to do? Do A? Okay, let's do A. You do A. Remember, the axis is coming in and out of the screen, in and out of the page. So do A. Okay, how'd you do? Did you get it? If you did, you can just go to the next one. But here's what I did. IA is the vertical and the horizontal, as we always do. The axis for the vertical rod is about the end, so that's 1/3. I didn't write the ml squared. For the horizontal rod, we have to slide the axis up till we get it through the center of mass. And when it's up there, it's 1/12 ml squared, right? I'm using the parallel axis theorem for this one. So that's 1/12. Then how far did I have to move it? I had to move it from the center of mass all the way to here. That's a distance of 1L. So it's ml squared. So I didn't write the ml squared, just the 1. And so we have 1 plus a 12 plus a third. That's 4/3, 5/3, 5/12. 1 and 5/12 is 1.41666 repeating. And since the problem says 3 significant figures, make sure you read that. We want to report the answer as 1.42. If you put in 1.416 or 1.4 or 1.417, it won't like it. Okay. B. B is easy enough. This axis is through the center, 1/12. That's axis through the end, so 1/12 plus 1/3. Here, 1/3. Ooh, this one's a little tricky. We got to move it this distance, right? If we take this axis and we want to put it through the center of the horizontal rod, the vertical rod, excuse me, the horizontal rod is about the end, so it's 1/3. We got to move it here, so we got to get that distance, right? Because when we move this axis here, using the parallel axis theorem, you'll have 1/12 ml squared plus m times the distance you moved it, that distance squared. And this is going to be the same thing here, and the same thing here. And this looks like it's the same as this one. Really? It's exactly the same. That's odd. Okay, so there's no difference. So what's that distance? Go ahead, get it. Okay, here it is. I just thought of a clever trick. I hope you did too. So we have a triangle, right? We're moving it from here to here, so that's L over 2, that's L over 2. And so we have L over 2 squared plus L over 2 squared. Square root gives us the hypotenuse. But actually, when we put this distance in, we got to square it anyway. So all we need is c squared. All we need is the hypotenuse squared. So if we take c squared equals a squared plus b squared, and a is L over 2, and b is L over 2, and we square those, we get L squared over 4, L squared over 4, and we end up with 1/2 L squared. So that's what will go in there. If you want to actually know what that distance is, well, it's L over the square root of 2, but every time you use it, you're going to square it anyway. So just leave it squared, and it shows up twice in this problem. Okay, let's move on. Okay, one more rod problem. Now, how do we get the inertia of something that's not a point? Because all we really know is how to get the inertia of a point mass, and if we have a series of point masses, but a rod isn't a point. All right, well, what happens if we just approximate it to a point? So it doesn't look like a point, but if we called it a point, we wanted to measure like, oh, what's the distance of the rod? You'd measure to its center. So if we think of the rod as having all the mass located at the center, we artificially make it a single point, and the axis goes through the center. Then when we do I equals mr squared, we'll see that r is 0 because the axis and the mass are in the same location. That's kind of like spinning the rod along its axis. It has no inertia. So we get 0. So that's not very useful. So what are we going to do? Well, let's split the rod into 2 pieces. Now that still doesn't look like a point, but it's a little bit smaller. And how do we think of this as a point? Well, we think of the mass, which is half of the mass, m over 2, all located at this point. And the other half of the mass, m over 2, is located at this point. And each of those points is a distance of L over 4 from the axis. So now let's find out what the inertia of it is if we separate this into 2 point masses. See if you can do that. It's just an algebra problem. Okay, there it is. This piece has a mass of m over 2. And if we measure to its center, it's a distance of L over 4, right? That's 1/4 of the length. And we square that. And the other piece is the same thing. And so we get m over 2, L squared over 16, m over 2, L squared over 16. And when we add those two together, we get 1/16 ml squared. Not bad, actually, right? Well, you say, well, the answer is supposed to be 1/12. Well, 1/16 isn't that bad, considering this is pretty crude, right? And when we did it with 1 point, we got 0, so it's not that far off. So let's do it for 4 pieces. See if you can do it for 4 pieces. Okay, I love doing this problem. It's so fun. It works out so nicely. So for we have 1, 2, 3, 4. So for 1, that's m over 4, right? Because we broke the m into 4 parts. And the distance, these are 1/8, 2/8, 3/8. So 3/8 L, got to square it. And this is m over 4. And it's a distance of 1/8, the length of the rod. So L over 8 squared. And then this is going to be the same as that, and this is going to be the same as that. So we just need to double this. Right? We just need to double this value. No reason to go through all that writing. And when you multiply this out, that's 64 times 4 is 256. I mean, the 3 squares to 9, and the 8 squares to 64 times 4, 9, 256. This is 1, 256. So that's 10 over 256. And then we get it again, so we get 20 over 256. Which is 10 over 12.8, which is 1 over 12.8. Oh my gosh, look, it's just 4 pieces, and we went from 1/16 to 1 over 12.8. We're actually getting closer and closer to that 12. And guess what? When you do this, no surprise, it'll even be closer. And how do you get exactly the 1/12? You divide the rod into an infinite number of pieces and you add them up, and that's calculus. So before you look at my answer, see if you can do it. If you're a calc buff or you like doing calc, see if you can do this problem. It often is probably done in Calc 2 anyway. But if you don't care, you can skip this, or if you just want to see how I do it, here's what I do. The rod is the integral going from negative L over 2. We'll call this x equals 0. And we'll go from negative L over 2. We're going to integrate all the way to L over 2. And we're going to take the position of every dm. So what are we doing? We take a little slice of the rod, and we call that dx, because the distance from the center to where each piece is, right, is a distance x, either a negative or all the way to L over 2. And so what I did was, rather than integrate from negative L over 2 to L over 2, I just go from here and double it. So 0 to L over 2. And the distance from the center to each piece is x. And I got a dm, so I got to change the dm to a dx. Otherwise, I can't integrate. So let's take a dx. How much mass is in the dx? Well, if we break the rod into 4 parts, we have 1/4 each, the length of each part divided by the total length times the total mass. So we take the dx, and whatever fraction of the total length it is, we multiply that by the total mass. Or another way of thinking of it is, the total mass over the total length is the mass density. And if you multiply that linear mass density times the dx, you get how much dm you have. So the dm is m over L times dx. So we change the dm to dx. M over L are constants. That's the total mass and the total length. We bring them out of the integral, and then we just do this very simple integral x squared dx, which is what? 1/3 x cubed. So there's the 2m over L. There's the 1/3 from the integral. And 0 L cubed over 2. 0 cubed is 0. And L over 2 cubed is L cubed over 8. And when we process all that, there it goes. There's the 1/12 ml squared. Just what we were hoping to see. So the last 7 problems involve this apparatus. It's the same apparatus. This is just a drawing of it. There's a base, which we ignore because it's light and low mass enough and frictionless. So there's 3 items that we need to account for. The bar, we know how to deal with a bar, and 2 masses that are small enough, located, they're small enough that we can consider them point masses. And this is an apparatus that we'd have used several times in lab had we been in lab, but you weren't. And generally the way we accelerate it is we wrap a string around the base and then put it over a low friction pulley, low mass, low friction pulley, where we don't have to worry about the pulley in this case. And the mass falls to the floor and the 2 things accelerate. So there were 6 problems on this that have randomized numbers. You'll all have different numbers. And then the last problem on this, which is a set of questions embedded in one question. So anyway, the first part of, I think it's number 13, asks to get the angular acceleration. And so you go to your kinematics equations, and you know how many revolutions this goes through, and you know the time, so you can use the third equation from group 2. So there's more than one way to do this, but I think the easiest way is just to use this equation, number 3 out of group 2. And since omega initial is 0, it starts from rest. It simplifies to this, and you just want to put it in radians. So each rotation is 2 pi radians. Okay, and then the next question will be delta y. And since we know the number of rotations, you can just use, there's 2 ways of doing it, but if we just use that S equals the angle in radians times the radius, we can take the number of rotations in radians and multiply by the radius of where the string is wrapped around. Right? So, and also you can think of it, if this goes through 4 rotations, say, that's 4 circumference, and each circumference is 2 pi, and 2 pi times r is each circumference. And so that will give you S, or in this is from the equation sheet, right? But that's delta y. In other words, this mass will fall the amount of string that unwraps from the hub, and the amount of string that unwraps from the hub can be found by this, because the length of string that comes off is equal to the number of radians times the radius of that hub where the string is wrapped. And once you have the angular acceleration, you can, of the apparatus, you can get the tangential acceleration of the string or the edge of the disk, and that will be the acceleration of the string. The linear acceleration of the string will be the acceleration of the falling mass. So you can actually do it 2 ways. You can get that tangential acceleration of the string, and which is the same as the mass, by just taking the alpha and multiplying by the r. Or you could use this equation where you have delta y, since you now know delta y, equals Vy initial t plus 1/2 t squared, at squared, right? The third equation from the regular kinematics equations, and you would get a similar equation. You would get that the acceleration is 2 times the delta y over the t squared. And if you really want to be careful, you could check both ways and make sure you get the same thing. Once you know the acceleration, you're ready to get the tension force of the string. But be careful, I'll show you a mistake that people often make. So you try and get it. What you want to do is draw a free body diagram of the mass, do some of the forces in the y direction, and use that to find the tension in the string. And be careful, the tension in the string is not equal to mg. That's the mistake you make. Why? Because the mass is accelerating. And since it's accelerating down, there has to be a net force down. So in this case, the tension in the string will be less than mg. Only if this were falling at a constant speed would the tension be the same as the weight. So draw the free body diagram and do that and get the tension in the string. Okay, here's what you should have gotten. Notice when I draw the free body diagram, the tension force is not as long as the mg, because I know there has to be a net force down. And so I write down Newton's second law, and then I write down what the sum of the forces are. Ft is positive, mg is negative, and I put a negative sign here because the acceleration is negative. You've got to be careful about that. And when I do the algebra, I get that Ft equals m, I factored the m out, g minus ay. So that means it's less than mg, which is what I said. It has to be less than mg because it's accelerating down. And it's less by the amount of ay, and ay, of course, is what we found in the previous section. And now that you have the tension, you can get the torque on the apparatus. So what I've done here is I've taken the apparatus and tipped it on its side so we can look at it from, say, the bottom up. And so here's the hub where the string is wrapped around. And the string comes off. I show it because we're looking from the bottom. And that is the tension force. And it acts from the distance from the center to the tension force is the radius of that hub. And so the r is the r of the hub, the F is the tension force, and you can see that the sine of theta is 1 because it's 90 degrees. That gives us the torque, and once we have the torque, now we can find the inertia of the apparatus. See if you can do that on your own. And so finally you see here that the sum of the torques equals I alpha, and so we solve for I. I is the ratio of the torque that's applied to the acceleration you get. That's the whole idea of inertia, resistance to acceleration. And of course the sum of the torques is just the one torque we found, because there is only one torque, the string, acting on the apparatus. So notice we have two ways of getting at the torque, and we actually, in a normal lab, we would do this. We do the experiment that we just did, and we measure the torque that we applied and how much acceleration we get, and that's kind of like how you determine torque. You pick something up and you twist it with your hand, and you could feel how much resistance or inertia there is. The other way is to use this set of equations to calculate it. So in problem 19, we choose an entirely different way to do it. And here we're going to consider that the rotational inertia of the entire apparatus is the rotational inertia of the bar plus the inertia of the two masses. And since the masses are the same distance and the same mass, we can just, rather than do each one separately, we can just multiply by 2. And the inertia of the mass, the inertia of the bar, of course, is 1/12 ml squared. We know that from earlier. And the inertia of each mass, thinking of it as a point mass, since it's fairly small, just treating it as a point mass, we simply get plus 2, because there's 2 of them, m r squared, where r is what? R, of course, is the distance from the axis to the center, since it's not really a point mass, to the center of the cylinder. But usually we measure the distance from center to center of the two cylinders and divide by 2 to get that distance r from the axis to the mass, and we can calculate it that way. However, at the end there's an additional question. Let me do a drawing. Suppose instead the cylinders are close to the axis. Now they are actually big compared to this distance to the axis. So now we treat them as a cylinder. And so to get the exact inertia of this thing, we don't treat it as a point mass, we treat it as a cylinder, and we use the parallel axis theorem. So we take the axis and we move it from the center of mass of the cylinder over to where the actual axis is. So this is the real axis, and it's not through the center. So we use the parallel axis theorem, and that way we can get the exact inertia without any error due to the fact that we're calling it a point mass. So see if you can do that. So first of all, notice that a cylinder and a disc are the same thing. A cylinder is just a narrow, tall disc, or a disc is usually a flat cylinder. And so whether it's a disc or a cylinder, the equation for its inertia is 1/2 mr squared when the axis is through the center. So when we use the parallel axis theorem, we say I is I center of mass, where the axis is here, plus how far we move the axis to the real axis from the center of mass. And that distance is what we would use if we considered this a point mass. In this case, that's the distance d that we move the axis. So if you're understanding what I'm saying, the correction to treating this as a point mass is this factor. So the md squared is what we would get if we treated it as a point mass. And so whether this is big compared to that is what's important. And you'll see when you do the problem, if the cylinder is close to the axis, then this correction is not trivial. But as the cylinder gets far away, that additional amount of inertia becomes less and less significant. All right, long assignment, long video, everything's been covered.